Our first speaker is Dr. Huettel, who is a coastal oceanographer, and his research focuses on biological and biogeochemical processes at the seafloor. Just to let y'all know, I forgot to mention that behind on your agenda are the speaker bios. So if you guys want to learn more about them, you can get more information about them on the back of your agenda, which are also located at the table. And so he is currently at Florida State University in Tallahassee, where he is presently a faculty member in the Department of Earth, Ocean, and Atmospheric Science. So without further ado, Dr. Huettel, please come up.
Well, thank you very much, Monica, for the nice introduction. Welcome, everybody. Thank you for your interest, and I thank the organizers for inviting me. So what I'm presenting here is, of course, not my own work. I mean, of course, I'm part of it, but it's a group effort. And so it's a collaboration between Florida State University and Georgia Tech, where we collaborated with Joe Koska and Kostas Konstantinidis. And we had a large group of students that had to dig a lot of holes in Pensacola Beach. And some of them are mentioned here that were specifically very active and participated in the research. There were a number more, but
sorry, you're tall.
That's quite all right.
There you go.
And of course, I should not forget the funding that allowed us to do all this research that came from GOMRI and NSF. So when the oil came to shore in June 2010, you were shocked and I was shocked. I'm a coastal oceanographer, so I saw the environment and I couldn't believe how it looked. And of course, this beach is a tremendous resource for the region, for tourism, also for the fishermen. And nobody really knew what's going to happen to all this oil. You can scrape it off the surface, but everybody knows that crude oil is a substance that does not degrade very well and contains a lot of toxic substances as well. And so the big question was, what's going to happen? What's going to happen to us, to the region, to the ecosystem? And if you looked at the literature, there were some examples from Exxon Valdez and also from European coast and so forth, but none of that is directly comparable with here with our Pensacola coast. You can remove, and this is a picture that I took on June 30th when I was here. There was a time when Storm Alex was in the Gulf and throwing big waves at the shore. You can remove these, excuse me, these big chunks here. There were some as big as office printers. So that is something that you can grab with the shovel. And the surface then was cleaned, not only by the waves, but also by crews that cleaned up the big mess on the surface. But each wave, and you may see that the foam is a little brownish, each wave threw water on the shore that contained some of particulate oil and also dissolved substances that came from the oil. And the waves dispersed the oil. It's not only chemical dispersants that can do that, can also be done by physical forces like waves. And so each wave brought this rim of oil onto the sediment surface, and then it also penetrated into the sediment. And if you look at the sediment cross-section here, then you realize that if you have a closer look, that this is not the white that you have below here. And this is a little close-up that shows a little bit more clear, hopefully. This is on the sediment below where it was affected by oil, and above you see the brown stain on these grains. So when oily water that does not contain big chunks of oil, but little particles and also dissolved substances, penetrates through the sand and leaves some oil on these grains that pick it up. So oil attaches very nicely to sand. If you ever had the chance to grab this stuff, which you should not do, there's a sign, don't touch, then you realize that this stuff, especially when it's relatively fresh, is pretty brittle. So it's not something that you can easily extract without destroying it. So we went there and started research because I'm a coastal oceanographer. I work on these shores, and I was very much interested in what's going to happen to all this oil that was buried in the sediment. Because as said, at the surface you can remove it, but how do you remove 2 feet thick layer of oil contaminated sand? You cannot do that. You remove all the beach basically. If you look at the concentrations in the clean sand, the hydrocarbon by mass is very small. This is background that comes from outboard engines and oil platforms. Stuff washes ashore all the time a little bit, also from combustion processes at the shore. And then you have this deeper layer, this oil-stained layer, where you have an oil film on all these sand grains. I'm going to show it in a minute, and small oil particles. And so still the oil is less than 1% by mass. Now the oil has a density that is about 1/3 of that of sand, so it's about 3% by volume. And down here, where you have these agglomerates, that's how they are called, you may have about 1/4 of the volume of oil in the sediment. And so it's not a lot, but it's still substantial in terms of what it can do to the environment. Below that, you have relatively clean sand, but we also could show in our experiments that if you run water through the sand, like from waves or from rain, you can wash out some of the more soluble oil components, and they end up down here. A look under the microscope or stereo lens shows you that even if the grains are covered by oil, they look almost like the clean grains. These are white. It's actually quite nice to look at them under the lens because it looks like raw diamonds. It's almost pure quartz. That's why the tourists love our beaches, the white snow. There's hardly anything in it. And then after the oil water washed through it, they became brownish like this. If you look at these agglomerates, then you realize, it's maybe hard to see on the slide here, but there's actually liquid oil between those grains. And that bakes it together, that makes it cohesive. This stuff is a little bit cohesive, a little sticky, but it still falls apart. Why is this important? Well, this offers a very large surface area. So you have a little grain that's covered by basically a molecular film of oil, offers a lot of surface area for bacteria to degrade this. And bacteria are ultimately what degrades this oil. So bacteria have a lot of access here, less access here. And I'm going to explain that in more detail. So what we did, we have our students out here, John DeGardio and Will Overholt here in the trench, digging these 10-meter long trenches over and over and over. We came on a monthly basis, basically, and dug them from basically the high water line up to the shore dunes where we did not find any oil anymore. And you can see this consecutive vein of oil, basically. It's a layer. It's basically the initial layer of oil that was deposited in June, a second layer shortly afterwards, and then some mixed sand that was deposited by storm, but also by the cleanup crews that moved sand back and forth. And we took these cores, took them back to the lab, sliced them up, and analyzed the oil. And then our work was interrupted because we had a lot of people also watching us, and then they came to the conclusion we have to do something about the buried oil, and they came with this deep cleaning operation where they removed this upper layer of sand. You can see it here. They have the bulldozer that removed about 1 to 2 feet of sand, ran it through these sifters, and then this sand was redeposited where it was taken from. Now, if you heard what I just said about the brittleness of this stuff, if you run these agglomerates through a sifter like that, that is usually used to do gravel, then it's pretty clear that most of this stuff was disintegrated in small particles. They got a few of these big chunks out, and that thing probably worked like a potato peeler, that the big chunk then became a very little chunk, and that was removed. But this was deposited on the beach, and you can see here a time sequence. This was the initial picture. These were centimeters sediment depth, 2 layers, as I mentioned before, the brownish yellow stained sand. And then shortly afterwards, this was a deep cleaning in October 2010. And after that, you had a homogeneous layer of brownish sand that was due to this cleaning process that mixed up everything. And then some leftovers of this layer in here. This was maybe not intended, but at the end was a positive thing, because again, it made big chunks of oil to little itty bitty ones that increase the surface area for bacterial deterioration of the oil. And then 1 year later, we basically saw that in the profile, we could not find oil anymore. And that's a bold statement, because once in a while we ran into a little tar ball that was way down here. The stains you see here are from iron or detritus, but this is not oil. And that is reflected here in our concentration measurements. These are total petroleum hydrocarbons, initially a lot at the surface. Then it was buried pretty quickly due to storms, but also by shifting sand over it manually by cleanup crews. And then by the time this cleanup came, already a lot was degraded. And then there was a long tail with a little bit of oil was still persisting, but pretty much after a year, we were down to background values. And that's shown in this picture. It's a little confusing. I agree with that. I will guide you through it. So this is the time axis. This is a hydrocarbon Hope-Payne ratio. And that is done because, of course, if you dig a trench, you cannot dig it always at the same spot. And the oil was not distributed totally evenly. So you take a reference, and this is this Hope-Payne that does not degrade very well, although it does a little bit. But if you take something that doesn't degrade very well, then you can take the other components that degrade very quickly and compare it to that. And with that, you get an idea on how fast these lighter components degrade. And so what this shows is basically the total hydrocarbons in this black line, and the aromatics, or cyclic components that includes the polycyclic aromatic hydrocarbons, which are partly toxic, and then the aliphatic ones, propane, butane, that degrade relatively quickly. And this is a logarithmic scale. So initially we had about hundreds of milligrams per kilogram sand of oil, and that decreased very rapidly within a year to background, which is about 1 milligram per kilogram of sand, or less even. So that is a pretty constant decrease on a logarithmic scale. So if you would plot that linearly, it would be a typical decay curve. But this suggested that this oil film, this small stuff, degrades very rapidly because there's this large surface area that is available for the microbes. And the microbes reflected that. So initially, so these are measurements done by Joel Kosker's group with the bacteria. So initially, these big black blobs are the ones that reflect the abundance of bacteria in the oiled sand. The yellow ones are bacteria in the less oiled sand, but we did not have really a clean control because oil was blown over the entire beach. So there's still a little bit of oil in this, but much less than in these big blobs. And you see that initially we have enormous growth of bacteria. There were blooms basically of oil degraders. And when this cleanup came, this gray bar, that changed dramatically. That the bacteria were mostly associated with these layers where there was concentrated oil, and when that was dispersed, that changed dramatically. It came back as the sediment was mixed with ambient sediment, it was not so polluted. The diversity, which is this red line, increased again, and these enormous numbers of bacteria went back to normal. So after this cleaning, we observed that the situation normalized. What made the degradation so quick, relatively speaking, if you compare it to Exxon Valdez, for instance? The warm temperatures in the Gulf. So this is sediment depth down to 50 centimeter depth. We have up to September 25 degrees Celsius in the 80s. And that is, of course, great for bacteria that love warm temperatures. Likewise, moisture is needed for bacteria breakdown. So that's why you dry stuff if you don't want to have it degrading. There was enough moisture in the sediment, even in the dry beach sand. Bacteria need about 1% moisture, and you can see that all over the place we have at least that moisture. So those circumstances were great for bacteria and bacterial breakdown. What else is needed for bacteria? The aerobic breakdown. So breakdown of oil in the presence of oxygen is the fastest. If you put oil in a bottle and you close it, no oxygen gets to it, you can put it in a shelf and your grandkids will still have it. And that will not degrade, at least not at a considerable pace. It's very different when you have oxygen present. So in these layers where we had oil, we saw a decrease of oxygen. These are oxygen profiles vertically through the sediment. So where there was oil, there was less oxygen. And that indicated that the aerobic bacteria were very active in using that, because sand, of course, is very permeable, you know that. What's interesting with these profiles, that they did not decrease at depth. You would anticipate that. Typically when you have a permeable sand or a sediment, you see a decrease and go someplace to zero. It didn't do it. It actually increased. And that brought the hypothesis, well, there's a mechanism that pumps oxygen in there. What could that be? Well, the tides, of course. So we put chambers on the sand, and where we had oxygen, where we had oil in, so here there's oil, and here there's oil, and no oil, no oil. When the water level creeped up in the beach, so when you dig a hole, as a kid, you probably did that, and you see the water level in there, so that responds to the tide, because the sand is very permeable. And that acts like a water level coming up in the beach. It's like a piston pump. So the air is pushed out, and when it drops, it sucks air in. That was the hypothesis. And that's what we see reflected here. When there's oil present, more CO2 comes out and less oxygen out of the beach when the water level rises, as here. So what it boils down to is this. Water level drops, heat and oxygen goes in, water level comes up, moisture and CO2 is pumped out. And if you have that through this layer over and over, every tidal cycle, right? It's breathing. It's like a big animal breathing. So you can compare that beach really to a breathing organism that inhales heat and oxygen and exhales CO2. And with that mechanism, you keep the oxygen in the sediment around the oil and accelerate the degradation. Now, as said, sand looked clean 1 year after oil came to shore, but once in a while we found this. And that's, of course, disturbing, and it's pretty clear. We know that oil degrades not very rapidly, so big chunks of oil will not go as quickly as a very thin film on a sand grain. So what did we do? It's not trivial to investigate that, because you cannot just pick up tar balls at the beach and put them in an analyzer, because they wash up all the time and you don't know where they come from. And even if they come from Deepwater Horizon, they may be in a submerged oil mat where it's excluded from oxygen, so they will not degrade. And as soon as they come to the beach, they start degrading. So you cannot really do that. You have to have a reference. So we picked up a whole bunch of these agglomerates, homogenized that stuff, put them in these stainless steel tea strainers, put them on a pole like that, always in pairs, 10 centimeter difference in depth, and put 10 of those into the beach. And then we took them out at 1.5 month intervals initially, and later on we spaced it a little because we wanted to see how that stuff degrades. And sure enough, you see a degradation. Initially, you can, first of all, you see a color change. So this was initially relatively brown, and that's due to the polycyclic aromatic hydrocarbons. They fluoresce as well, and then later on it became pretty black. And what you see is that the carbon content, so the most trivial thing here that you can measure is, it's not trivial, excuse me for that. So the clearest thing you can measure is just carbon in the sand. If you assume that the original carbon content of the sand is very low, in these, I showed you the clean sand, there's hardly anything in it, it's 0.001% carbon maybe, so the rest is oil. So you can measure just carbon by combusting that and measuring carbon in it with an element analyzer. You see that the carbon decreased. And you also see that the alkanes, so the long chain, not the cyclic, the long chain hydrocarbons decreased dramatically. They are chewed by the bacteria, they love them. And likewise, the PAHs, of course, we had some outliers. Here we caught another tar ball that came in later with our T-ball as well, got contaminated. and then the fluorescence reflects what the polycyclic aromatic hydrocarbons do, because those are the most fluorescent materials. Degradation rates in the sediment, as we have these different balls at different depths, we could tell that they were not equal, but at the depths where there was most of the oil, the degradation was highest because the bacteria were happiest. There was moisture, there was warm temperature, and there was also nutrient available, which increased with depths because it's brought in by the seawater. Now, the question is, why can these tar balls degrade relatively rapidly, assuming that in the big balls you don't have air? Well, that assumption is faulty. If you pick up this stuff on the beach, put it under the microscope, this is what I showed you earlier, but under the microscope it's hard to see on this picture, but there are holes in this. Not all the big pores are filled by oil. And if you allow a computer to analyze this picture and tell you wherever there's a hole that is as big as a sand grain, should mark it white, it looks like that. So all these white areas are spaces with air. And so if air is in there and air can circulate, so that when we measure permeability of these things, you can pump air through it. They are also exposed to this tidal pumping that I mentioned before. So that's why this stuff, even these more concentrated agglomerates, would degrade in the beach at a much slower pace because it's a function of surface to volume ratio, but they do degrade and faster than at the Exxon Valdez. Now, if you have these regressions here, they can be linear or nonlinear. You can put a function to it, and then you can use them to predict, well, how long is this going to take until it gets to background, or this one, until it gets to background. And that's what we did, and then you come up with these projections. So the carbon, which is the most obvious thing that clearly shows, and there are all these arguments that the oil can convert in other substances that are not caught by the instrument that we're using, for instance. If you look at just the carbon, it's a pretty clear answer. So the carbon would go to background, which we now here defined as 0.1% of the original carbon. If that is projected to the future, then we have about 34 years until this is to background, these big golf ball sized tar balls. That's how long it takes for them to degrade to background. The other stuff, the alkanes that are more degradable, but bacteria go faster. Within 10 years, you may have that degraded as well as the polycyclic hydrocarbons. If you take the same golf ball sized tar ball, and that's what we did, we took some of the material and kept it in the lab, put it in the cabinet, closed the door, let it sit there. No beach sand, no moisture, no light, no temperature. We analyze those, then it takes about 100 years and more for that to be degraded. So that's the beach effect. It makes this 1/3 of the time span by having the bacteria, the moisture, the nutrients, and so forth. Otherwise, it would take at least 100 years. Those are pretty conservative values because, of course, we have also environmental factors that we did not integrate in our 3-year time series. There may be a big storm that mixes up the beach, takes oil out, and for that very reason, it may be faster. Or there could be a calm period and a big chunk sitting there on the beach, and that will take hundreds of years to degrade, like we see from the X-Stock, where there's still some of these oil chunks sitting in the beach and in the water. So with that, I'm done here. And yeah, so my conclusion is surface volume to ratio is critical. It makes a lot of sense. Hydrocarbons in the beach sand contained with small particle aggregates and oil films decreased to background within a year. It's basically because it's so thin of a film that the bacteria can very effectively eat it. If you have a golf ball sized sediment agglomerate, then it will take approximately 30 years. A lot of that stuff was removed by cleanup crews, but in some areas they left the stuff in, like where birds were breeding or for pickens, for instance, where it's protected. So there, if you dig it up, you will find that in the next 10 or 20 years. The tidal beach breathing is probably very important. So when you have this up and down of the water level, then it brings the oxygen in that's so critical for the microbial breakdown. And so the microbial community is key, and the beach provides basically a good environment for this degradation to happen, because sand, as you know, is used in a swimming pool, filters, using to clean up water. All this is because the sand has this large surface area where the bacteria can attach, where stuff gets stuck, and then the stuff can be degraded very well. And with that, my students, thank you. Thank you very much for your attention, and I understand questions are later.